Welcome to The Explainer. Today, we're going on a seriously fascinating journey. We're going to start way up high looking at the global macroeconomics of the electric vehicle industry, which, by the way, is right in the middle of a massive, historic shift. And then, we're going to zoom all the way down to the literal atomic structure of a battery cell. We'll see exactly how molecular engineering is setting up the winners and losers of this totally new era. So get ready, because the landscape of global transit is changing faster than ever.
Okay. I want to kick things off right here with this number, 55%. In the first quarter of 2026, BYD, which is an absolute titan of the EV industry, well, they saw their net profit absolutely plunge by just over 55% compared to the previous year. I mean, that is a shocking drop to its lowest profit in more than 3 years. So why? Well, because the Chinese domestic market is currently locked in this brutal, margin-crushing price war. It's basically a knockout stage right now, and even the biggest players are taking some really heavy hits.
Now, to actually understand why this is happening, we have to look at the highest macro level, government policy. See, for over a decade, China's 5-year plans explicitly listed new energy vehicles as a strategic emerging industry. That meant funneling billions in subsidies to build a world-leading supply chain. But in the 15th 5-year plan, covering 2026 to 2030, EVs have officially been excluded from that strategic list. Yeah, the government's focus has completely shifted to things like quantum tech, biomanufacturing, and nuclear fusion. So the EV sector is now waking up to the reality of massive market oversupply, but without the safety net of those foundational subsidies.
Okay, let's dive into this. Here's our roadmap for today's explainer. First, we'll look at the Chinese EV squeeze. Second, record low battery prices. Third, Europe's push for battery independence. And finally, the silicon anode breakthrough. Part 1. The Chinese EV squeeze and the end of the golden era. So, the world's biggest EV market is navigating the really painful end of a heavily subsidized golden era. Let's take a look at the financial reality check for BYD. Not only did their Q1 2026 profit fall to $561 million, but their operating cash flow practically collapsed, dropping over 67%. And look at that third point. This is wild. In 2025, government subsidies accounted for over 38% of BYD's net profit. As those dry up and domestic prices keep getting slashed, BYD has to find totally new ways to survive. Their playbook? A massive overseas push. They're expanding rapidly into markets that offer higher profit margins, like Europe. In fact, they're literally building a plant in Hungary right now, specifically to bypass a 27% European Union tariff on China-made imports.
Moving on to part 2. Record low battery prices, the silver lining.
Now, if you follow the money, China's brutal domestic oversupply has actually created an incredible silver lining for the rest of the world. According to Bloomberg NEF, average lithium-ion battery pack prices have fallen to an all-time record low of just $108 per kilowatt hour. That's an 8% drop from the previous year. And get this, it's happening despite the fact that the underlying battery metal prices actually went up. The industry has basically been able to absorb those material costs because of just immense cell manufacturing overcapacity and cutthroat competition.
Now, what's really interesting here is the breakdown of these costs. At the top, lithium iron phosphate, or LFP batteries, average a remarkably cheap $81 per kilowatt hour. That chemistry, by the way, is heavily dominated by China. But check out the regional differences at the bottom. While the average price in China is $84, North America is paying 44% more, and Europe is paying a staggering 56% more for battery packs. So the big takeaway here is that while batteries globally are cheaper than ever, Western automakers are still sitting at a massive cost disadvantage simply because of their reliance on imported tech and much higher local production costs.
Which brings us to part 3. Europe builds battery independence, the fight for technological sovereignty.
The West is definitely waking up to the fact that it just cannot rely entirely on imported Asian batteries if it wants to stay competitive. So how is the rest of the world actually responding to this huge price disparity and technological dominance? Well, they're fighting for technological sovereignty. They are literally building their own supply chains from the ground up.
Let's see how this translates into real-world action. Take Volkswagen's battery company, PowerCo. They've just commissioned a massive gigafactory in Salzgitter, Germany. And their strategy is actually pretty brilliant in its focus. They're starting with a 20 gigawatt-hour capacity, which, to put that into perspective, is enough for 250,000 cars. They are standardizing their production around what they call unified cells, designed to give 10% more energy density while still allowing for different internal chemistries. Plus, to meet new climate priorities,
This whole factory runs entirely on 100% renewable wind and solar energy. That alone saves up to 115,000 tons of CO2 every single year. VW's ultimate goal? To cover half of its own standard cell demand right there with locally made cells. All right, part 4, the silicon anode breakthrough, zooming into the molecular level.
Here's the thing, though. Simply building factories isn't going to be enough. To survive in this hyper-competitive post-subsidy era, companies are going to need a massive technological edge. So we're zooming all the way down to the molecular level. For over 30 years, nearly every lithium-ion battery has used graphite as its anode material. But graphite has basically reached its physical limit. Enter silicon. Silicon is the ultimate challenger here because it offers a 10-fold higher specific capacity than graphite, 10 times. Replacing graphite anodes with silicon is absolutely the most promising pathway to dramatically improving batteries today. We're talking about potentially boosting practical energy density by 30 to 40% at the cell level. In the real world, this means cars that charge in under 10 minutes and drive significantly further on a single charge.
But wait, if silicon is so amazing, why aren't we already using it everywhere? Well, to understand that, we have to look at why graphite works so well in the first place. You see, graphite naturally forms in two-dimensional sheets. When you charge a battery, the lithium ions slide perfectly into the little spaces between these sheets, a process called intercalation. It acts kind of like a highly stable parking garage for the ions. When it's fully charged, the graphite only expands in volume by about 10%, and then it neatly shrinks right back down when discharged. It's incredibly stable over thousands of cycles.
And this right here brilliantly illustrates the molecular nightmare of trying to use silicon. When lithium ions flood into a silicon particle, the silicon doesn't just gently expand. No, it swells by a massive 280%. When it expands that much and then tries to shrink back down, the particle literally shatters. It fractures. In the industry, this is known as pulverization. Once those broken pieces lose electrical contact, the battery's capacity fades incredibly fast, and the whole battery basically dies after just 50 to 200 cycles. And honestly, that is exactly why current commercial batteries only sprinkle in a tiny fraction of silicon mixed in with mostly graphite.
But we are finally seeing a breakthrough here. Companies like Psionic Energy have developed some seriously cutting-edge chemistry to solve this exact expansion puzzle. Instead of trying to force the silicon not to expand, which is impossible, they're creating a stable, porous environment within the battery using novel binders and additives. This actually allows the anode to flex and breathe during the charging process. It accommodates that massive 280% expansion without fracturing the particle or damaging the cell structure. What does this mean for us? It means we can finally pack way more silicon into the battery, unlocking that ultra-high energy density, all while maintaining a long, stable cycle life. A real game changer.
Which leaves us with this final thought. We started out today looking at the macroeconomics. China ending its massive subsidies, profits plunging, and the West scrambling to build these huge gigafactories to secure their own supply chains. But the ultimate battleground, it might not just be about who can build the biggest factory. It's really about who controls the chemistry inside the cell. As the era of easy money ends, molecular mastery, specifically the ability to tame silicon, might just be the defining factor that decides the next global EV champion. So what do you think? I really hope this explainer gave you a clear, structured view of how interconnected this incredible industry truly is. Keep learning, and I'll catch you on the next one.